a few more examples of looking at geometric series. So we have this series n equals 2 to infinity, 3 over 7 to the n. All right, so this is a little bit of a sneaky one because we do have to do some algebraic sort of preparation. And a lot of the other ones, R and A, were readily available to us pretty easily. All right, so here's what we're going to do. We're just going to rewrite this series as series n equals 2 to infinity. And I'm going to move the 3 on the outside, and that's going to be 1 over 7 to the n. Well, not 3 to the outside, but 3 off the numerator. Now, we know that 1 is equal to 1 to the n, all right, because we can multiply 1 by any number of 1s, and it'll still be equal to 1. So really, this is the same thing as 1 to the n over 7 to the n, all right? So, and this only works with 1, okay? You can't just pick any number. And now this is the same as the series n equals 2 to infinity, 3 quantity, 1/7 to the nth power. All right, so sometimes you have to do a little bit of algebraic preparation to be able to make it fit the geometric form. Now, in this case, if I substitute 2 back in to find what A is, all right, so to find A, that's going to be, so to find A, that's when n equals 2, because that's the first term. That's going to be 3 times the quantity of 1/7 square, and that's going to be 3 over 49. So hold on to that, okay? R is going to be equal to 1/7, and clearly the absolute value of 1/7 is less than 1. So what we can say is that this does converge. Okay, so it converges. And now what we're going to do is we're going to find the sum because it does converge. Okay, so the sum of our formula A over 1 minus R is going to be 3 over 49, which we just found, divided by 1 minus a 7th. That's the same thing as 3/49 divided by 6/7. All right. And then finally, if we simplify that, all right, this is the same as 3 over 49 times 7 over 6. All right. And then we can do some cross canceling if we really wanted to. All right. And I believe ultimately this just turns into 1/14, right? Because that's going to turn into a 2. And that's going to turn into a 7. So we should get 1/14 for that. But of course, we can always use Excel to check that. All right, so that's how we try to handle ones that kind of look like they're geometric, but they're not necessarily put in a form. We just have to make it fit algebraically. Right. This is another example of a series that looks like it's kind of geometric, but not quite. Here's how we're going to tackle this one. We're actually going to split this into 2 separate series. Right? So let's write this as the series as n equals 0 to infinity of 2 to the n over 5 to the n plus the series n equals 0 to infinity of 3 over 5 to the n. Right? So just splitting that into 2 series because we have 2 terms in the numerator. Notice that only works for the numerator. This first series we can rewrite as n equals 0 to infinity of 2/5 to the nth power. That's pretty easy. This second one, we can pull the 3 off to the side, just like we did in the previous example. And this would be 3 times 1 over 5 to the n, which is the same thing as 1 to the n over 5 to the n, or 3 times 1/5 to the n. All right. Now, what we're going to do is we're going to check to see if both of the series converge. And then if they both converge, that means that there is a sum. So we would just find the sum of each and then add them together. Right? Right here, R is equal to 2/5. All right. And the absolute value of 2/5 is less than 1. So that one's good. Over here, R is equal to 1/5. And clearly 1/5 is less than 1 as well. The absolute value of 1/5, that is. So R is 1/5, and the absolute value is going to be less than 1 as well. So because they both are less than 1 for the R, that means that because their sum would be convergent as well. So it converges. Okay. Now let me call this R1 and R2 since we're dealing with, it's the same series, but we broke it up into two, right? That means we need an A1, all right? Which means that we're going to substitute 0 back in and we need an A2, right? So A1 is going to be equal to 1, all right? So we just substitute 2/5 back in. That's 2/5 to the 0 power. And then over here, A sub 2 is going to be equal to 3 times 1/5 to the 0, or 3. All right, so A1 is 1 and A2 is 3. And so now what we can do is we can figure out what the sum of both of these series are. Okay, so let me refresh this really quickly. All right, and then we just rewrite really quickly what we have. Okay, so A1 was equal to 1 and A2 was equal to 3. Right? And we had that R1 was equal to 2/5 and R2 was 1/5, right? And what that means is we're just going to go ahead and find the sum for both of those, okay? So let's call this sum sub 1. That's A over 1 minus R, so 1 over 1 minus 2/5, which is going to be 1 over 3/5 or 5/3, right? So keep that in mind, that's sum 1, right? Now for sum 2, that's going to be 3 over 1 minus 1/5, which is the same as 3 over 4/5 or 15/4. And then finally, what we're going to do is we're just going to add those together. Okay, so sum 1 plus sum 2, that's going to be equal to 3/5 plus 15/4. All right, common denominator, I'm sorry, 5/3, not 3/5. All right, so that's going to be 5/3, excuse me. All right, if we got a common denominator of 12, that would be 20 plus 45 over 12. All right, it's just by multiplying each of those. So that's going to end up being 65/12. All right, and that's probably as good as we can get with that. So again, if you have a series that looks like this, you might need to break it in two and then just maybe find that, make it the two series, determine if both of the series converge, and then if they both converge, then you can find the sum. Okay. One note before we stop this video: if either series diverges, so if either series diverges, then the whole series diverges as well. Okay, so keep that in mind as you guys are going along with this. Okay, all right, so we have one more example of our geometric series, and then we can move on to telescoping types.